So I wanted to do a bit of an intro to microtonal terminology because there's a lot of terminology out there and it can get quite jargony and difficult to understand. And if you're reading the Zen wiki, there's clearly a lot of jargon on there and some of it isn't particularly well explained. And a lot of it is, but it could be nice to have a video to help follow along with to understand it anyway. So just a brief recap of what temperament is, because I'm mostly going to be covering temperament-related jargon. We like to hear notes in or near simple frequency ratios from one another, and so it figures that we try to create scales where we have a lot of them available. Using temperaments, we can treat intervals as having multiple approximations of different frequency ratios. So the diatonic scale is made by stacking ratios of 2 on 1 and 3 on 2, or approximations of them. And so we can stack 2 and 1 up and down endlessly. And so, we take the frequency and we can double it again and double it again and divide it by 2 and divide it by 2 and up and down. And give us a whole bunch of what we would refer to as the same note, because this is an octave. And a 3 on 2 is a perfect fifth, but I'll call it a 3 on 2 from now on because it can get confusing to say fifth and 3 and 2. And so I'm just going to call it a 3 on 2 ratio. And so the diatonic scale, we've got our octaves, and then we might start stacking these 3 on 2s. So we start by adding, we start with our root ratio, which is 1 on 1. The first interval in the scale is itself, of course. And then the next interval in the scale will be 3 on 2. And then the next one might be a fifth above that again. So, a 3 on 2 above that again. So we'll multiply that by 3 on 2, and that'll give us 9 on 4. And then we might want another 3 on 2 from this interval. We might want this one to have its own 3 on 2 to play above it because it'll sound nice. And so that'll give us 27 on 8. And we can keep going and get 81 on 16. And so you can see what's happening here is, even though we're adding this really simple ratio, we're just multiplying each one by this really simple 3 on 2 ratio, they're getting very complicated relative to our tonic note, relative to our base note that we're building the scale from. We have these really complicated ratios because you multiply the same number by itself a lot of times, and it becomes very large and it ends up with this complex ratio. And this number here in particular, 81 on 16, is actually very slightly sharp of 5 on 1. So 5 on 1 is a really simple ratio. It's almost as simple as 3 on 2 and 2 on 1. So it follows that our ears will hear this as a really nice simple ratio. And if you've got this 81 on 16 right next to it, and I'll show you how close it is in a moment, your ears are probably not going to hear it as 81 on 16. They'll probably hear it as an out of tune version of 5 on 1. And that's because, our ears are quite flexible in what they hear, and they're going to try to hear more simple ratios nearby being out of tune than these more complex ratios. So 5 on 1 we can also represent as 80 on 16. So these two are the same, and these two are similar but not the same. And you can see the difference. These 16s cancel out, and actually the difference between these two, or the ratio in between these two, is 81 on 80. And this is known as a comma. So it's a very small interval. 81 divided by 80 is quite small. It's a very small interval that appears when you're creating scales out of nice simple ratios. That identifies the difference or the ratio between something that it might be desirable to have this 81 and 16 because it arises from a chain of really nice intervals, but it might also be desirable to try to make it closer to this 5 on 1, which is a much nicer ratio. And so how do we deal with that? How do we deal with this 81 on 80 difference that might not be super pleasant to our ears to hear, it being 81 on 80 away from a much nicer interval? And so one way that we can do it is we can actually just make each one of these a little bit flat. So we push each one down slightly in pitch so that each one is slightly out of tune, it's slightly flat. But each one is flat specifically by 1/4 of this. And so when you add them all up, you've taken a quarter of 81 and 80 off of this and a quarter off of that. So that's half of the error has been taken down now. and a quarter off of that, so now a third of the error has been taken off. 3/4 has been taken off. And then the final quarter taken off here, which means that actually, in this case, stacking this 3 on 2 times 3 on 2 times 3 on 2 times 3 on 2 has actually given us exactly, so in this case, it would be exactly, or I might do that in a different color. It's given us exactly 5 on 1 when we've tempered this comma out, and that's what it's called. When we shave off a little bit of this comma, so we might, if we were slightly flat here, we might want to increase the pitch of these all slightly to get it closer, but in this case, they're all slightly sharp of the interval you want, and so you shave them all down, and that's called tempering this comma out. So it's saying this is a tiny little interval between an interval we don't really like the sound of and an interval we do. This interval is a practical interval that arises as a result of some process we've done. And this interval is an interval that we want to magically appear by breaking the math slightly. And so that's what really we're doing with temperament, is we're sort of fudging the math a little, making everything a little bit out of tune so that we can have access to more nice intervals that we like. So, we've just by multiplying together 2 on 1s and 3 on 2s, we've now got an interval that has a 5 in it, which normally in math you can't just do. And yet we've done it by tempering it out.
Taking something great and ruining it a little so you can have more of it.
And so, this process of tempering is very useful as a way of slightly detuning some things to give us new intervals. So this chain of 3 on 2s and 2 on 1s gives us the diatonic scale. And it has, in this case, 2 characteristically important intervals. And that is the 2 on 1. So I've sort of just been assuming along here that you can multiply any of these by 2 on 1 and move them up and down an octave. And we haven't done anything by tempering these 3 on 2s down in pitch slightly. We haven't done anything with the 2 on 1. So the 2 on 1 stays exactly the same as it was in just intonation. And now by making all of these slightly flat, this 5 on 1 interval is now exactly the same as it is in just intonation. So by applying this temperament, this is specifically called a mean tone temperament when you temper out this comma in particular. But by tempering it out, we've made 5 on 1 exactly the same as just intonation. So 5 on 1 and 2 on 1 in our scale are the only intervals, and anything you can get from combining these, are the only intervals in our scale which are exactly the same as just intonation. And these intervals are called Eigenmonzos. And so just for completeness, this is a comma, not the only comma. Any small interval could be a comma, or even large intervals. If you use long chains, you could spread the comma out over a lot of intervals. So it could be large, but in this case, that's a comma. And detuning each of these down gives us a temperament. And yeah, so you might hear the word Eigenmonzos thrown around. It's really not as complicated as it sounds. It's literally just these intervals, which in the particular temperament we've done, tempering out a comma, stay the same as just intonation. And so this is specifically in quarter comma mean tone, where we've taken 1/4 of this comma off each of these intervals to give us this 5 on 1. In quarter comma mean tone, our Eigenmonzos are 5 on 1 and 2 on 1, and anything you can get from them. So 5 on 4 would also be an Eigenmonzo, as far as I understand in the terminology. But the Zen Wiki is super unclear on it, but that's my understanding. Is 5 on 4 is also perfectly in tune. 5 on 2 is perfectly in tune. 2 and 5 is perfectly in tune. So any interval you can get from multiplying or dividing these. Now, this 81 on 80, it helps to be able to represent, let me pick a new color. It helps to be able to represent complicated or more complicated ratios like this, and even more complicated ones, in a simpler way that helps tell you about how it came about. So we can just dissect this into a bunch of prime numbers. So we can say 81 is 3 times 3 times 3 times 3, and 80 is 2 times 2 times 2 times 2 times 5. And so this is the prime decomposition. This is the prime factorization of it, which is to say that, these are the smallest whole numbers you can break down 81 into. You can't break it down any further because 3 is only divisible by 1 in itself, 2 is only divisible by 1 in itself, and 5 is only divisible by 1 in itself. So these are prime numbers. 81 is obviously not prime because it breaks down into these numbers that multiply together. 80 is not prime because it breaks down into these. But if we break it down to this prime representation, it gives us a really interesting, useful tool. And so let's write down here the prime numbers: 2, 3, 5, 7, 11, 13, 17, 23, and so on. So these are the prime numbers. You could just learn them, or you can look them up or whatever. But they're the numbers that can't be divided into any other smaller whole numbers. And now what we can do is we can actually just list what we've got here as numbers, or as a number of prime numbers. So on the top we've got 4 3s, so we could write 4 here. We've got 2 4s and a 5, but they're on the bottom, so we're going to say that we have a negative number of those in our number. So we have a negative 2 of, negative 4 of these. We have negative 1 of these, and we don't have anything else here, and so these are not particularly important. And so if we put a square bracket here and an arrow on this side, and I can put the arrow wherever I want. I'll just put it here, but I should probably put it all the way up here because we don't have any of these other primes. What we've created is called a Monzo. So this is a Monzo. It's a prime factor representation. Now it's not to be confused with the Eigenmonzos. They're the ratios that don't change. This is a Monzo representation of this number here. So let me simplify it. I'll remove these zeros. The Monzo is negative 4, 4, negative 1. And we draw it like this. And all it's simply telling us is if we take each column, this is the 2's column, this is the 3's column, this is the 5's column, and then we don't have any 7's or 11's or 13's or anything. It's just saying that we've got 4 2's on the bottom, 4 2's on the bottom. It's saying we've got 4 3's on the top, 4 3's on the top, and 1 5 on the bottom. That's the negative sign. 1 5 on the bottom. And so we can multiply these together really easily and give us this representation, and that is 81 on 80. So this is another way of essentially just writing 81 on 80. And now we know this really interesting piece of information about it, which is that any intervals which combine these primes together will give us 81 on 80. So I'll give you an example. The Monzo for 3 on 2. 3 on 2. The Monzo is negative 1, 1, 0. And that's because this is the 2's column, so we've got a 2 in the bottom. That's why it's negative. And this is the 3's column, so we've got a 3 on the top. And we don't have anything in the 5's column, and so on. And so I have ended it there. And I've added this 0 for a good reason, and that's because our Monzo for 5 on 1 is 0, 0, 1. And that's because we have nothing in the 2's column, we have nothing in the 3's column, and we have 1 in the 5's column. Because remember, these are our each column is the next prime number. And so we can see how if we take 4 of these, we times this by 4. So essentially we've taken a stack of 3 on 2. We've taken 4 of them. We get a new Monzo, which is negative 4. So we've gone 4 times of these. We've got negative 4, 4, 0. And if we take the difference between these and that, essentially we're just subtracting this one from this one. And so if we subtract those two, we get a new Monzo, which is negative 4, for -1, because remember we've divided by this. We're comparing 4 of these and 1 of these, so we're subtracting this one. And we can see -4 for -1, just as we had before here. -4 for -1, which we know just by multiplying these primes together, by multiplying 4 3s on the top, and then 4 2s on the bottom and a 5 on the bottom, 81 and 80. So we've really simply shown that 4 of these 3 on 2s and 1 5 on 1 are separated by this comma, this 81 and 80 comma. And so the Monzo representation here that we're doing just makes it really easy to compare intervals, and especially if you get much more complicated intervals. You can just do really simple arithmetic on the primes, just really simple adding and subtracting, and that'll tell you a lot of information about how they relate to each other. So it's a really neat way to decompose these intervals into the simplest parts and compare those. And this goes without saying that any intervals which multiply together to give another interval will have Monzos, which when you add them together will add up to that interval, exactly as I've shown here. So I'll give one more example. The Monzo for 9 on 8 is -3 to 0, and you can check my math on that. And the Monzo for 10 on 9 is 1 -2 1. And if we divide this one by this one, all we're doing is just subtracting each value from there. So we get -4, because -3 minus 1 is -4. 2 minus -2 is 4, and 1 minus 1 is 0 minus 1 is -1. And so we've got the same the same Monzo here, which means that we've got the same interval. It's 81 and 80 again. 81 on 80. So the difference between 9 on 8 and 10 on 9, and when I say the difference, I mean the ratio between them, is 81 on 80. And 9 on 8 and 10 on 9 are both whole tones. And this is the greater whole tone and the lesser whole tone, or at least that's what I understand them to be called. And by making them the same, you're essentially taking an interval in between. So by tempering out this interval, that is by saying that these two are the same, we get mean tone. And that's why it's called mean tone, because it's a tone that is somewhere around the average of these two, rather than having them as being distinct. Now, this leads to another use for this sort of prime notation. It's a bit different, but it follows very similar principles. So let's say we have 12 Edo, which is 12 equal divisions of the octave. So the 2 on 1 ratio is divided up into 12 equal bits. And so let's do our little prime representation again. So we've got primes 2, 3, 5, 7, and we know that. Okay, so just for clarity, what we're about to talk about is how many steps in the Edo it takes to get to this prime number, or approximation of this prime number. So we know that by definition, 12 Edo is 12 steps in the octave, or 12 steps in the 2 on 1 ratio. And so we can say that there are 12 steps to the 2 on 1. And then our closest approximation in 12 Edo to a ratio of 3 on 1, or 3, is 19 steps. And our closest approximation to 5 on 1 is 28 steps. And so on. And you can check the math. I've got a previous video called Sense to Fractions Conversion in Microtonal Music, and that will help you understand a little bit better, if you don't understand here, how to sort of take these ratios, which goes without saying, 2 on 1, 3 on 1, 5 on 1, 7 on 1, and find out how many steps in an equal temperament, or how many cents as well they're best represented by. So we can do this with any interval. We can find any interval in just intonation and find what our best approximation in 12-vedo is in steps. But I've done it with the primes for a particular reason, and that's because any other interval, as we saw with Monzos, can be made up by multiplying or dividing these primes. And because the steps of an edo are like sense, they're logarithmic, we can simply add or subtract the number of steps to get to that interval. So let's say you want to know how many steps our best approximation of the ratio 5:3 is in 12-vedo. You can say, okay, so the number of steps for 5 is 28, and the number of steps for 3 is 19. So we go 28 minus 19, which is 9 steps. And in fact, that is correct. So the best approximation of 5:3, 5 divided by 3, or 28 steps minus 19 steps, is 9 steps of 12-vedo. And so if we write out the mapping for each prime in steps, we get what's called a val. So if I put an arrow here, so it's the opposite way to writing a Monzo, and a square bracket here, that is called a val. And it's essentially just the number of steps to give each prime. And we can keep going on forever. And it's a really helpful way of then determining, okay, so in between each prime, you know, how many steps is that ratio? You know, if we wanted something like a ratio of 9 to 5, we could just use 2, 3. So we could do 19 plus 19 minus 28, and that sort of thing. And so this is what our val for 12-vedo looks like, and we can extend it out, like I was saying. By adding scale steps, we're multiplying the frequency ratios, and by subtracting, we're dividing frequency ratios, as I showed here. We can also use vals for rank 2 temperaments, so that's probably a topic for another video, so I'm not going to go into that here, but if you have any interest, let me know. So the val we created here specifically is known as the patent val. So I'll write this down. Val, and this one specifically is the patent val. And so the patent val, it really simply just means that we've taken the val here, we've taken the number of steps to approximate each prime frequency ratio, as the closest approximation we can get in the temperament. So 19 steps in 12-vedo isn't exactly, you know, a ratio of 3 to 1 in frequency. It's just very close, and 28 steps isn't exactly 5:1. It's just the closest that we have. Now, surprisingly, you don't always want to use the patent val. You don't always want to use this mapping that gives you the best approximation of each prime. Sometimes you want to use the second best or third best approximation for one of those. So consider the 13th harmonic. So actually, let's consider the octave reduced 13th harmonic. So 13 on 8. That's 840.5 cents. So in 12-vedo, the closest approximation we've got is 800 cents, because in 12-vedo everything is every step is a multiple of 100, which is 8 steps or 8 steps. So that's not very close, but nonetheless, let's say that this is our mapping. Let's say that we're mapping our 13 on 8 to this interval. Here, and so I'm not gonna talk in terms of patent val anymore, but essentially your 13 on 1, but because your ratios of 2 are all perfect, we can pretend that 13 on 8 is the same as 13 on 1, because the error will be the same. So let's say that we build a chord that has a major third in it as well. So the major third in 12-vedo is 400 cents, but in just intonation it's about 386 cents versus 400 cents or 4 steps as our closest approximation. And so this is a bit sharp, you know, so you compare 800 cents to 840, it's quite flat of the 13th harmonic, versus 5 on 4, which it's quite sharp of. It's much closer than 12-vedo gets to 13 on 8, but nonetheless it is still sharp. So what if we want a ratio of 13 to 10? That's just the difference between these two. That's a 13 on 8 divided by a 5 on 4. And so, just for clarity, 13 on 1 is 44 steps with the closest approximation, this one. And 5 on 1 is 28 steps. So 5 on 1 is 28 steps, and 2 on 1 is 12 steps. And so 13 on 10, you can say, well, it's one of these on top, so it's 44 steps, minus 28 steps, because 13 divided by 5, and then it's also divided by 2, because it's 13 on 10, not 13 on 5. So 44 minus 28 minus 12, so minus that equals 4 steps, or 400 cents. So essentially what this is saying is, well, our 13 on 10 using these approximations here, or using these numbers of steps that we've used to approximate it, it is 400 cents. But 13 on 8 is actually, 13 on 10 is actually 454 cents. Which is closer to 500 cents in 1280 than it is to 400 cents. If you look at it, it would round up to 500 cents if you had to round it to the nearest 100 cents, as you do in 1280. So despite using the best approximation for 13, the best approximation for 5, and the best approximation for 2 in steps, when we've actually tried to find what 13 on 10 is, we found a worse approximation. So under circumstances like that, it's worth considering whether you should use, a different approximation. And that's because despite the fact that these were the best approximations for each individual one, the 13 on 1 is very flat and the 5 on 4 is very sharp. And so it figures that the difference between them is going to be widened even more, and in fact is so far out of tune that you're better off using a worse approximation of one of these, because at least, if it, at least instead of using 800 cents, if you use 900 cents, even though that's further from this 840, it's sharp, and 400 cents is sharp, and so the errors might cancel out a bit more when you're doing 13 on 10 or 13 on 5. And so we might instead use not 44 cents, but we instead might say, well, 13 on 1 is 40 equals 45 steps. Even if this interval suffers a little, it can make other intervals in our chords sound a little bit better. So of course we can pick and choose, depending on the scenario, which approximation we want to use. If we want a chord with both 13 and 5 and 4 in it, it's worth saying, well, maybe we want to use this one, because even though this interval's worse, this 13 on 10 interval might be better, and it might make the sound of the chord sound a little bit more stable. And it really depends on context. It can, a lot of different factors can play into it. So 12 is an extreme example because it does such a bad job at approximating ratios of 13. But larger equal temperaments run into similar issues that are a bit more granular and finally, difficult to discern from the surface looking at them. And so we can define if we want to treat an equal temperament as though one of our primes uses using its second best approximation by adding what's called a wart. So we've got 12 Edo. And so simply writing the corresponding letter of the alphabet next to it, the letter that corresponds to which prime we want to modify, will adjust our val. So we start off assuming the patent val. So where's that? 12, 19, 28, 12, 12, 19, 28, and so on. And this is a patent val, and then we can modify this by adding a wart. So if we want the second best approximation of 13 on 1, instead of writing 12 Edo, we could write 12 F Edo. So F being, if we look at our list of primes from earlier, A, B, C, D, E, F. So let me write them. A, B, C, D, E, F, G, H, so on. And so if we were to write F next to it, then essentially what we're saying is, rather than using that, so wherever the 13's place is, I'll extend this out a bit. Rather than using 44 steps, 12F Edo uses 45 steps as our 13, and so gives us different approximations of the ratios between each of these primes. And if we wanted the second best mapping for 7 on 1 as well, we could call it 12DF Edo. And if we wanted the third best mapping for 3 on 1, I don't know why you would do that, because that would be the tritone. But essentially, say we wanted to use a tritone as our 3 on 1 ratio, we'd write 12 BBDF, assuming we also wanted those things. Edo. So we wrote that twice because we wanted it to be not the second best, but the third best. And any letters we don't write, we just assume that we're using the best. So this concept is known as consistency. So let me just sum these up. These are warts. But yeah, this concept we're looking at where, we have issues where some of the intervals are better tuned and some are the second best approximation is known as consistency. So if you can use the best approximations in an Edo of primes up to some odd number, while the ratios between them are also the best approximations available, we say that it is that number limit consistent. So 12 Edo is 9 limit consistent, which means that any ratio involving numbers less than 9 will be the best approximations available if we assume all the primes map to the patent val. That is, if we glue the primes to their best approximations, the ratios between them are also the best approximations available. Something like 31 Edo is 11 limit consistent, because up to 11 on 1, so up to 11 on 1, it approximates the primes either almost exactly or flatly, but it approximates 13 sharply. And so the errors, rather than cancelling out, go in opposite directions, and you actually end up with the ratios in between something like 13 and 11 becoming worse than the next best approximation. Become worse than another approximation available. And so that's the issue you get when the errors go in opposite directions. So consistency, in my opinion, isn't super important, but it's just something worth being aware of. So this is what I was talking about here is consistency. It's not always very important, but it is worth being aware of in terms of choosing intervals when using temperaments, because sometimes you might build a chord. Say you build a chord in say you're building it in 31 equal temperament. Because it's not consistent in the 13 limit, different chords might use different approximations or different number of steps to refer to the same interval, the same ratio, depending on the context, to try to make that interval sound better, because there will be multiple other intervals that relate to it, and at least one of them is going to have to suffer and be worse. So in the case of 31 Edo, I think so 13 on 8 is fairly good. Something like 13 on 7 or 13 on 5 is fine. But 13 on 9 runs into issues where sometimes you might have to use one number of steps to get 13 on 9, and sometimes you might have to use another. So sometimes your chord might paradoxically sound better if you make one of your intervals tuned worse. So let me check that I've covered everything. So I've covered what temperament is, the idea of taking a small comma interval between two different intervals that arise in a scale or that you're interested in, and making those intervals the same so that you can have access to more nice intervals than you would otherwise. So that's temperament. That's commas, these small intervals. Eigenmonzos are the ratios that don't change from just intonation when you apply a temperament to the scale. The Monzo, which is just a way of representing using primes as columns, a way of representing intervals that makes it easy to add and subtract these prime numbers, which result in multiplying and dividing the ratios. So it's just a very easy way of analyzing and comparing intervals. So we also talked about vals. We talked about patent vals and also other vals that we can use here by changing the mapping of each interval. We talked about warts, which are these little additions you can add to say, well, we want to use, the second best approximation of the prime corresponding to F, which, if you follow this little chart, is the 13th harmonic. And of course, we talked about consistency, which is the idea that ratios up to some, ratios involving numbers up to some number will always be their best approximations, assuming one particular mapping, and that you don't have to change the mapping. And so I think that pretty much covers everything I wanted to cover in this video. There's a lot more I could have covered, and I probably have spoken much too much already. But I'll cover some more jargon in future. But hopefully this is a good introduction to the kind of jargon you'll see when talking about temperaments, and specifically equal temperaments and rank 2 temperaments. You'll talk about this sort of thing as well. And so I might talk more about those in the future. But hopefully this gives you a bit of an idea of what these terms mean in context, and helps show how they're not really as complicated as they sound. They can, something like warts on the surface can appear quite complicated, but really if you have this handy little chart where you go A is 2, B is 3, C is 5, D is 7, list the primes, list the alphabet, really something like that is not all that complicated. Monzos is not all that complicated, using the same chart, just building intervals. Vals not all that complicated, you're just using the same chart again, except this time saying how many steps in the temperament it takes to get to that interval, and then you can add and subtract them to compare or to get ratios between those numbers. So none of it is all that complicated. It's all fairly straightforward and usable stuff that a lot of which you can do in your head. You just need to be able to understand this complicated terminology. And the brackets thing can be quite confusing. Sometimes I get confused when I see them. So the arrow is on this side for vals, but it's on this side for monzos. But yeah, at the end of the day, hopefully this has helped you to understand a little bit better some of this complicated terminology regarding temperaments, and how to use these tools to your advantage. Thanks for watching. Let me know how I can improve these videos, and make sure to subscribe if you're interested in seeing more of this sort of thing. Hopefully I improve over time in my explanations, but yeah, I hope you enjoyed. I will see you next time.